So in this lecture, we're going to look at our next functional group, the alkene. The alkene is a functional group classified as having a carbon-carbon double bond. Sometimes these molecules can be called olefins. It's kind of a fun word to say, olefin. But these are molecules with the alkene functional group. Okay, that's a highly industrial term. Something a little bit more popular that you might hear is unsaturated molecules. So unsaturated molecules are also alkenes. And that's because an alkene is a site of unsaturation. So sites, in quotes, I like to put sites of unsaturation. Okay. So we have these sites of unsaturation. What I mean by that is if we look at a molecule like this, I just made that, I don't know, some long carbon chain on a carboxylic acid. And then if I do the exact same thing, maybe with more or fewer carbons, and I add an alkene to it, I would call this a saturated molecule. Now, this is a molecule with a polar head group and a non-polar tail. We've seen this before. This is an example of a carboxylic acid resulting from the hydrolysis of a fat. So this is a fatty acid. And in particular, this is a saturated fatty acid. I say we've seen this before. That was with the soap unit because these things can be good detergents. This was the soap unit in organic chemistry 1. So this is a saturated fatty acid, whereas a molecule just like it with a site of unsaturation is called an unsaturated fatty acid. Okay, so that's where we might see the term saturated and unsaturated appear in kind of popular culture, I guess. Okay, so it turns out that alkenes have an opportunity for stereoisomerism. So alkenes can have stereoisomers. And these are, I would say technically they're diastereomers because they're non-mirror image stereoisomers, but another common approach would be to call them geometric isomers. So I'm going to write geometric / diastereomeric. So instead of diastereomeric isomer, you might just say diastereomer, for example. But either way, and we can have geometric or diastereomers. This is all due to the lack of free rotation or due to the inability for free rotation across the carbon-carbon double bond. Okay, let's look at a specific example of this. I'm going to consider an alkene of with 6 carbons, so this would be a hexene. We're going to put the alkene in the center carbon, and then we're going to compare that to a molecule that looks like this. These two molecules have the same number of elements, same number of carbons and hydrogens. I believe that's C6H12 probably, okay, if we counted them. Okay, so same number of elements, the same overall connectivity. So they're not constitutional isomers, but they are isomers because of the same number of elements. They're not conformational isomers because it's not due to a change in geometry due to free rotation over a carbon-carbon bond. Rather, these are just molecules that only differ in the three-dimensional arrangement of the atoms. So these are stereoisomers of each other. And they are that way because we can't do free rotation at that central carbon-carbon double bond. So these two methyl groups are forever close, whereas if I draw the hydrogens, you can see that the ethyl groups, I said methyl groups before, I meant ethyl groups, sorry. The ethyl groups are on the opposite side on the left-hand example and the same side on the right-hand example. So it turns out that a short or kind of a quick designator for this would be trans versus the stereoisomer on the right would be cis. Now where this comes from is the H atoms are on opposite faces or opposite sides of the CC double bond. Whereas in the case of the cis isomer, the H atoms are on the same side of the CC double bond. Okay. Now, this is another important term that's been popularized, and that has to do with cis and trans fats. It turns out that if you have two unsaturated fatty acids, so let's draw that long carbon chain again. So if we consider this fatty acid, this would be a trans fat, and trans fats are scary. They're really bad for you. They can cause a lot of issues with your cardiovascular system. Whereas cis fats, you don't hear them called cis fats too often, but cis fats are frequently found in places like plants and fish and that sort of thing, and they have much less of a negative impact. In fact, many times a positive impact on your metabolism. So this would be a cis fats. You don't hear cis fats too much, but trans fats are. It's important to be aware of them, and we'll talk about some sources for trans fats. Okay, so we have cis and trans to designate possible alkene stereoisomers. Now, what I want to point out is that there are some times where alkenes can't have a cis or trans label. So let's just write it this way. Some alkenes can't have stereoisomers. And what happens here is that on one side of the alkene, you have two of the same thing. So if we had something like this, where we have two hydrogens over here, if I said to you, are the hydrogens on the either side of the alkene, are they on the same side or the opposite side? You would say neither, because both of the hydrogens are the same. Now, similarly, if I put two methyl groups, we would say that neither of these, similar as before, because we have two methyl groups, two of the same thing on the right side of that carbon-carbon double bond, these can't form geometric stereoisomers. Okay, so we just don't label them with cis or trans, right? Well, what about alkenes that we can, that we put two groups that aren't hydrogen but are different from each other on one half of the carbon-carbon double bond? So if I said to you, is it cis or trans, you'd have to say, okay, I'm going to look at the alkene hydrogens and see if they're on the same face or the opposite face of the alkene. And here you would say, well, across the carbon-carbon double bond, there's only one hydrogen. Only one H. So that also means no cis or trans. We need two we need two hydrogens so that we can identify if they are on the opposite side or the same side of the carbon-carbon double bond. So we can't assign cis or trans there. But this is an important example because if we look at this, okay, and I'm just going to take the right side of the molecule and flip it. So now the ethyl group is pointing up and away, and the methyl group is pointing down and to the right on that right side of that alkene. these two are definitely stereoisomers of each other. So how do we label these? And I realize this is a bit of a review from Organic Chemistry 1, but that's okay. It's one of these important things that we have to be able to do, and it's pretty easy to learn once you see the rules. So how do we label this? We use the EZ nomenclature, and it's not to indicate its level of difficulty, though it's much easier than R and S for labeling stereoisomers, but rather it's E for integen or entigen, German, for opposite, and then Z for zusammen, or same. So it's just German for opposite or the same. So what we do is we, step one, we cut the alkene in half. So if we cut the alkene in half and we've got 4 different groups attached to it, I guess, we cut it a half perpendicular to the carbon-carbon double bond. And then in step 2, we label 1 and 2 priorities. So we do the prioritization. Let me spell this quick. We do the prioritization on the left and right sides. But we stop at 2. We only have 2 groups on the left or the right side, where 1 is the higher priority and 2 is the lower priority. Okay. And in step 3, we assign E and Z. If 1s are on the same side, then we have Z for zusammen, or same. What I like to remember is Z, same, Zide. Z, same, Zide. Okay? If they're on the same side, Z, same, Zide, it's Z. If 1s are on the opposite side, it's E. Now, the way I remember this is opposite starts with a vowel, and entigen or integen, sorry, is also, E is just a vowel. So the vowel corresponds with opposite, which also starts with a vowel. Okay, so let's do this on our examples. I'm just gonna, sorry, I know you're probably still writing that down. Just looking to make sure I get the structure right. So I believe it was this versus this. And again, you're probably still writing. Sorry about that. Okay, so what we can do is we can cut the alkene in half for both of these, prioritize the groups. I like to draw hydrogen because hydrogen always is the lowest priority. So on the left side, the hydrogen gets the 2. On the right side, the big propyl group, on the left side, the big propyl group gets the 1. Now on the left side, we're comparing a methyl group versus an ethyl group. The ethyl group is bigger, so it gets the 1. Remember, larger atom, or if they're both carbons, the bigger group kind of extending outwards. So we compare both of these. We see that the 1s are on the same side, on the right side. So that would be Z, same, Zide. And then opposite side, E, vowel, opposite starts with a vowel. And so we label this E and Z. Okay, so this allows us to label stereoisomers of alkenes in cases where cis or trans doesn't work. And in fact, this works for every alkene that can have stereo centers. So E and Z works for every alkene that can form stereoisomers. Every alkene that can form stereoisomers. And what this means is that it's better than cis or trans. And really all cis alkenes are just Z, and all trans alkenes are just E, but it doesn't go the other way. Not all Z alkenes are cis, and not all E alkenes are trans. Okay, so E or Z is definitely better, and E or Z is definitely kind of the approach to go with as you're looking at classifying alkene stereoisomers. What I want to do before we wrap up is to touch on iupac naming of alkenes, excuse me. So iupac naming of alkenes. So we have this alkene, let's name it. Number 1, locate the longest chain with the carbon-carbon double bond. And let's pick on an example that we were just using. So we've got our propyl group, and then pick on the isomer we identified as Z, and we'll make note of that. So number 2, name the parent chain. And I didn't do this, or I didn't do step 1 yet. So let me do that quick. So the longest chain in the molecule is going to go this way. And so this is the parent chain. 1, 2, 3, 4, 5, 6, 7. So we have 7, so that's heptane. Step 3 for naming is to cross out the ANE and replace it with an ENE. So the ane becomes ene because we went from having an alkane to an alkene. So our heptane now becomes a heptene. Okay, so we have a heptene. So number 4 is we're going to number the following. We're going to start with the substituents, which includes the position of the CC double bond with the lower number. So even though it extends across 2 carbon atoms, so we could label it based on my numbering 4, it extends across carbons 4 and 5. Sorry, zoom that out. Even though it extends across carbons 4 or 5, we would only include the lower number, which in this case looks to be 4. Now, the key thing with numbering the substituents is you want to check both directions and take the lowest numbers. So in my example, even though I have the numbers going 1, 2, 3, 4, 5, 6, 7, this gives us a 5-methyl and a 5-alkene. But if we number in the opposite direction, that is, instead of starting with 1, I end with 1. That is going from right to left instead of left to right. Okay, so here I would have a 3-methyl and a 3-alkene, because the alkene starts at carbon number 3, even though it extends across carbons 3 and 4. So this is sort of the way to go here. And then last is check for E/Z. And then in step, and then that was Z. We've already done that for this particular molecule. And now we're going to put it together. And here we're going to apply a lot of the rules that a lot of the basic rules from Organic Chemistry 1. So what I'm going to do, though, is I'm going to just go through, I mean, it's one of these things, you have these substituents, put them in order. If you have multiple of the same thing, add dies, tries, tetras with numbers, you'll get good at it the more you practice it. It's just one of these things. There's examples and problem sets, so just sort of work through it. But we're getting a little long-winded, so I'm going to call this, so what I'm going to do is I'm going to write Z, and I like to put it in parentheses, but you don't have to. I'm going to put Z dash because we're going to get to something new. This is going to be 3-methyl, and then 3-heptene. The 3 right before the parent chain is the position of the alkene, or the position of the CC double bond, a lower number only. Now, it turns out that some folks like to put the 3 in the middle of the parent chain name. So I would prefer the first iteration of this because I prefer the first iteration of this because I like having all dashes separating letters and numbers. We have that weird methyl heptene sort of thing. So I guess that wouldn't have a dash in there. Just is a little bit harder to read from my perspective. But if you write this down and it's correct, you have my blessing because it is technically accepted by some of the community. Okay. So that's iupac naming. There should be examples of that in the problem sets along with the old exams. I'll let you kind of dive into some of the deeper rules, but the alkene rules are sort of laid out in there. Okay, I'll see you next time.